That's for the deep ones. It's a new I have a bunch of code. It says right now it's just equal. But this one side, here the guy who's you buy it. Yeah, so like now I'm right up there's not right. Yeah, so that's been rebuild this because it was I think the icon. That's how it goes together. But not the plus. The thing is, like they're trying to know this. If you don't go through it all. Like, yeah.
All right, guys. 2 o'clock. So we're gonna get started. Today we are covering a very important topic. Actually, it's probably one of the most important lectures because it sets you on the right path, right? So you really have to understand this one. This is the perceptron. So it's the precursor to ChatGPT, to all neural networks. So the best analogy I can give you, if ChatGPT is your whole brain, right, and your brain is made up of neurons, so the perceptron is just one neuron you see of your whole brain. So that's essentially what it is, and that's what we're going to take a look at today. So this is really important, right? So building models that predict. So this is essentially neural networks. We will be covering neural networks for the next couple of weeks, the perceptron, Hopfield networks, and the multi-layer perceptron, right? So essentially, when you have these things, neural networks, there's like two things, A and B or whatever you want to call it, two functions, but there's two things you want to understand, okay? So one is to build a model that you give it an input and it gives you an output. That's called the inference part. But to get that inference part to work, there's a second component, which is the algorithm to learn, right? To something called the weights or the mappings between inputs and outputs. So there's two things. Today, we're not going to talk about so much about the learning part. And I just want you to focus on that inference part and understanding that really well. Does that make sense? So that's what we're going to look at. And that's the perceptron. So we're going to start with that. I have created homework 2, right? So homework 2, I'm going to give you probably 2 to 3 weeks to complete. It's a really important homework that I think you'll find fun, actually. So I'll start with that because that way I'll motivate a lot of what we're going to do. Does that make sense? So doing the homework assignment. All right, so we should be recording and everything. So I haven't provided the link yet to the homework, but it's here on the repo already. So I'll start with that. So machine learning foundations. And I usually have this folder called HW for homework. So I usually provide a lot of the information here. So essentially what you're going to do is you're going to do a web perceptron. Okay. So that's going to be homework number 2 for the semester. Okay. And my goal with this is that you really understand that inference part because you're going to build it. Right. So it's not going to work unless you understand how, and it's also not difficult, by the way. It's not a difficult homework. But I'm just, it's important that you build this. So let's click on this, right? So the web perceptron, essentially you're going to implement the perceptron inference function on a website using either JavaScript or PyScript with Python. So you can do one or the other. I would prefer that you do PyScript with Python, given that I'm going to give you the Python code. And I have a whole bunch of examples of how to use PyScript already on the GitHub, but you could probably do it with JavaScript too. All right, so what are you going to build? So this is a perceptron right there. Okay, let me see if I can get this thing out of the way. That's a perceptron. That's a neural network, in fact, right there. Right, a very simple one that you could actually build with electronic components. There's no chip or anything like that. It's pure logic. Very, very nicely done. So what it is essentially is this is obviously hardware. You're going to implement this in software on a website. Does that make sense? So what do you need? So let's think about how you would build something like this. This is going to be, so this is to give you some idea, this is an image, a picture. What image do you see there? A T. Very good. Yeah, it's a T. And I could write an L, I could write an E, kind of like that, right? So that's an image. You see, so you can totally do that with, on a website, just doing like a table and putting zeros and ones, and that gives you the shape. Obviously, you control this by just flipping these little switches over here. So again, you have some drop downs, on, off, on, off, on, off, on, off, and then you have your image. Totally doable, right? And then, you need to think about the other things. So the idea is essentially this is a perceptron that takes an image. The original perceptron was 28 by 28, I think, or 24 by 24, or maybe 40 by 40. I don't remember. But to keep it simple, this is easy enough, 4 by 4. And just represent little images of T's or L's and things like that. So obviously the class today will go over the code in Python and start to explain the ideas of the perceptron, right? Of understanding how it works, the precursor. So the perceptron was created, back in the 40s, like it, theoretically, and then this was built in 1957 or so. And from there, we've had all the progress up on, until now, today, with ChatGPT and DeepSeek and all that. So anyway, so this is simple. This is just a representation of these switches. That's an image. So essentially then each one of these LEDs is connected to one of these potentiometers. And the potentiometers just are a way, like a little knob, right, of having a value from 0 to 1. You guys see that? So basically what that means, we're going to learn that somehow the perceptron will connect this LED to that potentiometer, and this LED to that potentiometer, and this LED to that potentiometer, and so on. And so we're just going to essentially imagine that you take this value, which is a 1 or a 0, right, times whatever this is, and then that's a value, plus this one times this one, plus this one times that one, plus. And that's essentially a neural network. So you control these values of the potentiometer, multiply them by the corresponding value of the image, and that gives you a final result. And that final result essentially is what you see here, this thing here. Yes, sir. That's a good question. That's the bias. So we're going to see essentially that when you build this sum, right? So that's good. There's 17, right? You notice that. So each one of these LEDs has a potentiometer, but there's an additional one. So it's going to be, those 16 plus the last potentiometer for just the bias value. And we'll see the bias is something like when you have a line in a graph, you can just move the line in a direction. So there's moving it like this and then moving it like that. And that's the bias essentially. Yeah, go ahead.
That's not like limited to like lights. It could be for like value. It like determines how much electricity gets like flowed in.
This is to just physically represent how the perceptron works, the algorithm. This is a neural network essentially, but a very simple one. Later on, here right now, the LEDs are just going to be 1 or -1 or 0 or 1, true or false, whatever. But eventually we will see that neural networks can have any value, like 36, 77, and it still works. Do you see that? Yeah. So if you understand how this physically works, then you will understand the equations and everything else that we're doing. So, and that's why I want you guys to build. I'm going to elaborate. That's the whole purpose of the class today, is for me to elaborate on how this works. And you can build this actually at home if you want. I mean, get a whole bunch of potentiometers. That's all you need. So what I was saying is, this is the input, the image, a T. You set the switches for whatever you want. And then what you want to do is, and this is the important thing, let's say that you have a problem where you have T's and L's. You see that, a T or an L? So you want to classify the T's as positive, +1, just above 0. And you want to classify the L's as -1 or just below 0. Do you see that? So that's essentially this one here. So this little indicator, you can see at the center, it's a 0, right? So what you want is you want this needle to move in this direction if it's positive. So that's one class. And you want to create a model that associates for all t's whenever you give it a t, because remember, this t could be here, but also it could be moved by 1. You see, like the LEDs, oh, sorry. The LEDs could just shift to the right. So, you know, the T could be here, like the line could be that, right? And that's still a T. So you want to classify all T's in this very simple example as +1, and then all L's as negative. That's your problem. I just decided that's the problem, right? And so very simple. Very, you know, this is a perceptron, so don't expect anything more sophisticated than that. But the whole point is we want to build a model that whenever we give it a T, it's towards this side. And then whenever we give it an L, whether it's shifted or not, it's towards the negative side. You see that? So essentially, how do you do that? Well, in such a small thing, you would put T's in here, and because this is a circuit that you can, you know, think of it, it's running on batteries, right? So you can come in and you play with the switches and you make a T. And then essentially, this will move to the right automatically, right? Then you come in and you mess around with the switches over here, and you draw an L. And when you draw that L, you want this little arrow to move to the left side and be less than 0, so it's negative. Do you see how that works? So what's the key thing, though, for that to happen? So you know that you can control the switches, you know you can make T's and L's, and you know that you want this to switch to the left or to the right. But the key thing is, the key secret is you have to mess around with these knobs until that happens. So right now you don't know how to do that. So what you would do is just randomly try the knobs, right? Or maybe instinctively you might say, well, I'm going to make all the ones that are L negative. So you're going to make all these switches here, or these potentiometers, point in another direction. You know what I mean? So some to the left, some to the right, and you play with them. So that's what neural networks are. Neural networks are somehow, in a clever way, figuring out what the strengths of these potentiometers should be, which are called the weights, as we will learn later on. Does this make sense, guys? All right. Yeah, go ahead.
So when talking about one of these neural networks that like set its own weights,
Set its own weights.
is that where you said?
What do you mean, set its own weights?
That
Figure out, learn. Yeah. Okay. Set as in learn. Yeah. It has to
So-
learn these weights. Yes.
doesn't that mean we need to set some sort of initial value?
Right. You start at random and you have an algorithm to train it.
Oh, okay.
So that's why I said there's 2 parts. This is just the first part. Randomly set them, and you should understand that you've got one part of it, which is the inference part. You give it an image by flicking all the switches. You put a T in there, and it goes to the right. You flip these switches, create an L, and it goes to the left. You see that? So that it's doing the inference, and that's what you want. That's the behavior that you want. But to achieve that behavior, you have to mess around with these knobs, you know, like randomly or however you want to do it, right? And eventually you need to arrive at that behavior. Give it a T, give it an L. T, L. With very little error, essentially. So that teaches you one part of a neural network, which is the architecture from input to output. The second part of this is how do we, because, this is, okay, so you can maybe do this for an image that is 4 by 4, but images are 300 by 300 with, massive neural networks. So that's not going to be 16 plus 1 potentiometers. ChatGPT essentially would be 600, I think DeepSeek is 671 billion. So that means it would be 671 billion potentiometers that you would have to That's a correct analogy. So, it would be that many. So you obviously cannot do it manually. So we need an algorithm for that, right? And there's only one algorithm for that called stochastic gradient descent, which is not something we'll cover today, but that's what Geoffrey Hinton, they invented an algorithm called backpropagation that does that. You see that? So today we're not going to talk about that part of how to find the correct configuration of the potentiometers. I just want you to understand this part, okay? You give it an image. We're doing everything in hardware so that, this picture is hardware so you can physically imagine how it works. Now, what I want you to do is to do a website with this idea, okay? So that's going to be your homework number 2, okay? So you can do it in JavaScript, or I'll show you on Wednesday how to use something called PyScript with Python, and you can just leverage the code that I'm going to provide today. Okay? Any other questions? But yeah, so essentially that's a neural network. I mean, there's beyond this, there's just like a few additional details, but understanding this is pretty fundamental. Okay? If this was in a software environment, obviously this is similar to having a camera. The camera would take a picture of something. That would be this grid. This is black and white, obviously, because it's 4 by 4. If it was color, you would need 4 by 4 by 3 layers of it. And then essentially each one of these LEDs is multiplied times the value provided by the potentiometer. And then they're added. They're what is called linearly added, right? And then the sum of those is just one value, which would be this value here, somewhere between less than 0 or greater than 0. And that indicates if it's this class or that other. All right? All right. So great. So I think you guys get it, right? So we're going to get started with the Perceptron and how it works. So let's take a look over here. So where you see, yeah, here, I think. So it should be these. And I'll provide more links. So as far as hosting the website, you can use something called GitHub Pages. So we'll cover that as well on Wednesday. So you can go to GitHub and create your own website with something called Pages. So you'll deploy it there. And then, there's all these links, but I'll show you. So I'll do that on Wednesday because I didn't take a look at that. All right. All right. So that gives you the intuition, all right, of what we're going to do for your homework. So the goal of today then is we're just going to get started with how the Perceptron works, some of the key ideas of it, some of the problems and challenges, right, historically, and, of how it evolved into what we have today. All right. But it's all very related. Like a lot of the equations that you're going to see today are actually equations that you still see in deep learning. They're just, have more variables essentially. Okay. All right. So now that I did that, let's go back to the repo. So it's under neural networks. So neural networks is a long sequence, right? So we're going to be spending a lot of time on neural networks for the next few weeks. We're starting with the Perceptron. Then we have hop-field networks, then a multi-layer perceptron from scratch. And then we're going to start our PyTorch sequence, which will start with linear regression all the way to deep learning. Okay, so it's quite a bit of a long sequence. So it's under neural nets here. And you can see I provided a lot of the examples. Today we're looking at this one, which is called the Perceptron. All right, so let's take a look at some of the history of it. So the Perceptron was invented in 1943 by McCulloch and Pitts. They kind of theoretically thought about it. They thought about some of the ideas of it. But the first implementation was a machine built in 1958 at Cornell Aeronautical lab by Frank Rosenblatt. Okay. All right, and this was funded by Naval Research. And you can see there's some interesting things back in 1958 at a press conference, and there's still a clipping in the newspaper about this. Rosenblatt made statements about the perceptron that caused a heated controversy among the AI community. The New York Times reported that the perceptron, according to Rosenblatt, was the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, and reproduce itself and be conscious of its existence. So that was in the 40s, 58, right? If you look at it today, he was kind of right. So can computers or neural networks, okay, walk, maybe, but they can talk for sure. They can see, they can write. ChatGPT, right, can do all these things. Reproduce itself, they can make copies of themselves. And are they conscious? I don't know, but we don't know, right? But so even in 1958, people were already thinking about AI as an entity. So although now there were some problems, right? So the evolution of this has had periods of a lot of excitement and then periods that are called AI winters. So although the perceptron initially seemed promising, it was quickly proved that perceptrons could not be trained to recognize many classes of patterns. So this was initially, because the perceptron by itself, as I'm going to discuss it today, has some limitations, right? That's why we have something called perceptron and then a multi-layer perceptron, where it's an improvement upon the perceptron that is better, right? And so that's what we're going to study, that even today, if you look at ChatGPT, is based on something called transformers. And within the layers of the neural network of ChatGPT, you have layers called multi-layer perceptron layers. And those are essentially perceptrons that are multi-layer perceptrons that are used within the overall architecture of ChatGPT or a GPT network. So we've had several periods in time where the AI field kind of stagnates, and you have these periods which are called AI winters. So this happened from the 60s to the 80s, for instance. Those 20 years, there was like very little research in AI because of misunderstandings, honestly. And so, but then, you had like breakthroughs in 58, then you had a breakthrough in 84. And so that's kind of in the history of it. So I'll come back to this a little later. So let's go over here. So this is essentially the circuit for that perceptron that I just showed you, in case you want to build it. So let's take a look at the timeline. So as I said, in 1943, you have McCulloch and Pitts. They had like the original ideas of it. Then in 1958, you had Rosenblatt, who built the perceptron, and he implemented something called the perceptron learning rule. So the perceptron learning rule is equivalent to this idea of turning those knobs, okay? So, how do you turn the knobs? So as humans, we know, okay, we're going to turn them, but how do you translate that into an algorithm, right? And so that's the first time that we have some way of learning what those values should be, right? And that's called the perceptron learning rule, okay? So that's something that we will do in the Python code today, okay? So, but the perceptron learning rule is not backpropagation. Backpropagation is actually the algorithm that allows us to train something like ChatGPT today or those neural networks. That was not invented until 1984, okay? So this is Rosenblatt. Then in 1959, also, we have something, so kind of at the same time, another group was working on something very important, okay? And that is how to calculate those weights. So Rosenblatt invented something called the learning rule, but this guy, Bernard Widrow, and his PhD student, Ted Hoff, basically said, okay, let's use calculus to solve this problem, right? And so this is actually, so if you didn't know, actually, neural networks use calculus, right, to learn how to update the weights. So you don't need, it's very simple actually. So we'll just do a couple of examples of how that works later in the semester, and I'll show you the basic idea. But this was pretty fundamental. So in 1959, he was already thinking about how to calculate the weights in a smart way, but he was not able to solve it. So he was not able to invent the backpropagation algorithm back then. It wasn't until 84 when Geoffrey Hinton actually solved the problem, and his team. So you can see that that's here in 1984. Right? And then I just provided a list of papers. Okay. So we're going to start writing the code for this. Okay. So we're going to do the Perceptron in Python with Anaconda. And then after that, I'll come back to some of the, kind of explain some of the aspects of it. All right. So let's take a look. The code that I'll be using is here. So you can just get it from the GitHub. It's going to be in Machine Learning Foundations Neural Nets, and it's going to be this Jupyter notebook, basically. Okay. And then, as I said, I'll come back to discuss, because even though it's a simple thing, there's like a lot going on, okay, that we have to try to understand. So let's start our Jupyter notebook. Start Anaconda prompt. I'm going to go to the desktop. Okay, so here we are. So the Perceptron is not a very powerful algorithm, but it's got a lot of the elements that we will use later on for more powerful algorithms, such as the multi-layer perceptron or deep learning itself. All right, so let's start. So we did KNN last week, right? And we've looked at that algorithm. We're done with it, so you should, hopefully you understand it. Some of the students, actually, before I forget, they asked me to do something. So even though I have my algorithms in all these different folders, they kind of asked me that anything that I did in class that I put in a specific location. So if you notice in the Machine Learning Foundations repo on GitHub, I created this little folder called 2025. So everything that I do in class, I'll dump in here, okay? And that way you know exactly the thing that I did in the class. So for instance, the KNN algorithm that I did last Wednesday is here, okay? And today I'm going to work on this Perceptron, and then when we're finished, I'm going to load it here. And that way you can find the exact thing that I was working on during class. Although I'm referencing my own older scripts, so sometimes they'll be exactly the same. So in this case, we're looking at this one here. And although I have several, like this one, Perceptron, and this one, I'm only really going to use this one, the one with plots. All right. So we're gonna write a lot of these from scratch. Okay. So during the first third of the semester, I just want to write everything in NumPy. So up until the multi-layer perceptron, we're going to implement everything from scratch in NumPy. After the first exam, we're going to start using a powerful library called PyTorch so that we can actually solve like real world problems, right? So the first third of the semester, the focus is mainly in the focus is concepts and really understanding basic principles and foundations. During the second third is more about like being practical and actually using powerful tools. All right, so let's pick an Anaconda environment here. So I'm going to do Conda environment list. Conda environment list. So I think we're using we're using 33.7, right? I 30, yeah. So I'm gonna do conda activate I 37 2025 ITS 365. Okay, there we go. I'll do Jupyter Notebook. So one nice thing about neural networks actually is they all follow the same template. So you'll see me always, I'll have data, I'll have certain functions like the inference function, something called the activation function, the learning out function, and so on. And for the next 5 or so weeks, I'll be using the exact same structure. The thing that's going to change is I'm going to start adding libraries. We're going to make the neural networks more powerful, if you will. And today, as I said, we're starting with just one neuron, okay? Just one neuron is what we're trying to implement. All right, so I'm going to create a new Jupyter Notebook. And we're just going to start building it, and then we're going to start talking about it. All right, so here we are. I'm going to call this one in class Perceptron. Name it. All right, so let's take a look now at the code over here. I'm just going to copy this code. And I'm going to say here that this is, a perceptron. And actually there's the idea by McCulloch, then there's the implementation by Rosenblatt, and then there's like improvements that were made to that by the other guy, what was his name? Widrow. So Widrow actually invented something, an extension of the perceptron called Adeline. And my point is, all what I'm discussing today kind of touches on all three. Okay, so just be aware. But this is still before like the multi-layer perceptron. So essentially an advanced perceptron at best. Let me go back to that just so I have it as a reference. Yeah, so I will highlight like the very subtle differences between the pure perceptron and Widrow's perceptron, which is called, like I said, Adeline, and it's just an improvement upon it. So you can see the okay, so let's run this. Now let's run the libraries. So we're using NumPy, sklearn model selection, which we used already. If you remember the train test split function, we already used that in the KNN example to split the data. sklearn datasets, if I want to import some datasets. And then matplotlib, I'll be using matplot for plotting things like performance, etc., as needed. All right, so it executed, so all the libraries are available. We don't have to install any. All right, so now let's think about the structure of a perceptron. All right, so I'm going to have a function called fit, and fit is going to be the way that we learn. So that's those knobs, right? So remember in the example I gave you, you have an image, and then you turn the knobs, and then when you change it from a T to an L, the thing moves and it's either positive or negative, right? It provides the class essentially. So in the example I gave you with the knobs, you would do that manually. Obviously, the Perceptron did have a learning rule. All right. So they did provide, something beyond just randomly switching knobs. All right. And so that's the algorithm. That's what the fit basically means, is that process of finding a good set of the knobs, of how to turn the knobs. A good set of, turns, essentially. So that's going to be our fit function. We're also going to have something called the activation function. We're going to have a way of predicting, right? And various, other things like the graph. So let's start then with, you can see that most of it is happening in the fit function, okay? So let's start with just creating some data, okay? And we're going to go from there. So I'm going to create some data here that we're going to use. So this is the train test split. So I'm going to start here. All right, right there. So this would be equivalent to, so back here. Let me go back to the machine. So the way that this machine works is you put in a T, you want this to go that way. You then flip the switches and you make this an L, and you want this to go the other way, right? So what you do is you play with these knobs, kind of like you're just doing that. But in an algorithm, that's not how you would learn the weights. Instead, the way that you would learn the direction of these knobs, called the weights, is that you would give an algorithm a whole bunch of data, right? So you would give, for instance, examples of T's with this to the right. And then you would give examples of L's with the arrow pointing to the left. You see that? So let's say you would give 100 examples, right, of T's. In this case, we can only actually do 2 T's, right? We can do, I keep doing that, sorry. We can only really provide this T or the T that shifted a little bit, right? So that's all we can do because this is hardware. But obviously, if this was like software, we have more flexibility, right? But essentially, when you're training, you give examples of T's, 100 of them, and every single one of those, the arrow would be a little bit to the right, greater than 0, right? And then also, during the training, you would give examples of L's and the associated direction of the arrow, which would be a little bit to the left. You see that? So that's how it's going to work, guys. So we give data to the model, and then the model needs to use that data to kind of adjust these knobs. And then at the end, it's going to have the right setting for all the knobs. Yeah? All right. Excellent. So that's what we're going to do. So we need to give it lots of data in kind of like a loop kind of situation, and then it's going to learn. So let's see if we can start building that. The first thing I'm going to do here is I'm going to create a very simple data set. All right. I'm going to use this function from sklearn. I'm going to use a function called make blobs, and this just allows me to randomly create some data that follows a specific pattern, right? So in this case, I'm going to create X and Y. It's going to have 150 samples. Each sample, X, is going to have 2 features. So remember, we already talked about what that means, right? So we got samples, which are rows, and columns, which are features, right? So these are just the descriptors of the sample. 2 pixels, for instance, right? And then we just say that there's 2 centers, and we provide the standard deviation. So it's like it creates 2 distributions, and we're just going to sample from those 2 distributions, and one's going to be class 1, the other one is class 2, so that they're distinguishable, All right, so let's take a look at that. So I'm just going to generate that. Done. So now, remember, you can always take a look at the data just by printing shape. You can see that I have 100, it's 150 by 2. This is my X matrix. 150 samples, 2 features. Got it? All right. And I have the Y's here. Which is 150. So these are the labels. So if I print Y, the values are 0 and 1. If it's -1 or 1 versus 0 and 1, it doesn't matter. They're different. And the algorithm will learn, but we could change the zeros to -1. Definitely can do that. So the analogy here is that the X here represents, going back to the machine, the X is this, right? The images of T's and L's, okay? And the Y represents basically this little needle, whether it's positive or negative, 0 or 1. Got it? So that's how the machine works. All right, so we've got our data. We can add a few more cells here. All right, once we have our data, let's go back to the original script. So I've done the shape of this, the shape of that. This I did already, as you saw last week with K and N. We're just going to split the data into train and test. Oops. There we go. So now I'm going to take my X and Y, and I'm going to do a 80-20 split, right? So I'm going to use 80% of the data to train the Perceptron, and I'm going to leave 20% of the data to test it, to see if it worked, right? So we would hope that it works. Yes, sir? 80-20, 50-50 is probably a bad idea. You want to give it a lot of the data so that it can learn well. So yeah, that's usually why I do it. Okay. It's some in WECA, I think the default was like 10%, but that may not be enough because we only have 100. So the thing that the key factor is here, we only have 150 samples. Now I could have created more, like because I'm creating these randomly, so I could have just added an extra 0 here and then have 1,500 samples. But let's just, for now, keep it like this. It's just common practice. Go ahead.
Is there any sample you have the data set of this?
Of sklearn?
Yeah.
RAM. How long you're willing to wait for it to learn. If you did WECA and the MLP, probably for the homework, right? It's taking a long time.
Yeah.
Yeah, so I would say that. I mean, I think if I give it 100,000, it's going to work. If I give it 10 million, it might run out of memory. Any other question? Although that's why we want to use an efficient library like NumPy, though. So NumPy will allow us to have more samples. All right, so we're going to do the split. Okay, so that worked fine. So then as you can see, and this is exactly what we've done before, x_train dot shape. And I'm going to do a print here. And then print x test. And then I'm going to do print y train. And then I'm going to do print y test. All right, so if we print these, this should be very similar. Oh, yeah, I didn't print the shape, sorry. To what we did with Iris last week. There you go. So it's 120 by 2, 30 by 2. So that's the number of samples, the X's. And then the number of labels is 120 and 30. Okay? So that's done. Now let's go back to the original code. So we might, you can print this again, but essentially it's going to be zeros and ones, the different labels that we want to learn from. And then essentially now we would do the following. So this is where a little bit of math will come in, just very little, but you'll see how I will connect the math to this machine that I gave you here. Okay, so I will represent with a math equation what this is doing here, and it should be pretty simple. And it's something that's very familiar to you already because it's the line equation, right? So you've seen that in algebra. All right, so let's go over here. So where is that going to be? I'm going to create this function called fit. Okay, and what this function does is it's going to take the X train, Y train data, the training data, and it's going to use it to figure out those knobs, right? Which we're going to call, starting now, we're going to call weights. And they basically need to have values, right? Values which could be from -1 to +1 somewhere. They could be 0. And then essentially that means that that value is not important. Or it can be -1 and it means that, it's important, but in an inverse way. Like something goes up, then that comes down. Or if it's a +1, then it means something goes up and that thing goes up as well, right? So we're going to look at those relationships. You can also think of weights as strengths to say how important that feature is for the class, for predicting the class. Okay? So that's what we're going to be looking at. So we give it the data, and then what it returns is really interesting. It's going to return this thing called the weights and the biases, which are going to be variables that we use in an equation. Okay, so we're going to learn the inference equation today, which is what I said. So when you're training neural networks, there's two big things, two equations. One is called the inference equation. The other one is called the loss function. All right, and we're going to use a loss function today, but that loss function is something that changes throughout as the problem changes. Okay. And the inference equation essentially is the neural network that we're training, the machine. All right. So we'll see that. So this returns the weights and the bias. And you had that question of why 17 instead of 16, because we need this, which is that 17th value. And then these will be those 16 values, essentially, the weights and the biases. All right. So I can't run this yet because I haven't defined the fit function. That fit function that I'm going to define right now is the perceptron algorithm, essentially. So now I'm going to make some room up here. And we're going to start defining the fit function. So I'm going to copy this part here. Okay. I'm going to do def, right? Fit train, colon, and then here we're going to, we know that this model returns the weights and the bias, right? So which are the parameters together, both of these two things are called the parameters. And this is whenever you hear, oh, DeepSeek has 671 billion parameters. That's it, right? That's the intelligence of a neural network right there. Whether it's ChatGPT or this little Perceptron, it's the same. Okay. Right. And then what changes is the architecture. Yes, sir. Oh, did I? Oh, yeah. Thank you. Right. All right. So obviously in here now, we need to take a look at the perceptron algorithm. Okay. So here we need to add a very important concept that we will see throughout the semester, which is the matrix multiplication. So you remember at the beginning of the semester, I gave you about 100 problems, right? It was not a homework to submit, but I said, do these manually. And then when you're done, just go back and do them again, right? Whole semester. So in one of those, you may remember there were some matrix multiplications, right? Because you guys did all of those, right? All of you did them. So when you were in several actually of those problems were the matrix multiplication. So this is where we're going to start using it now. And essentially is a way to take data and multiply it times weights to arrive at something. Okay. All right. So let's take a look. And so right now, first I'll go over the code. We're going to get it to run. I'm going to talk about it just so that we know how everything fits. And then I'm going to go to the whiteboard and we're going to start like writing a few notes just so that we have a better understanding. Okay. So let's go here. So as you can see, we've got the function. So now we need to go back a little bit to this here. All right. So let's take a look. So we are going to, I'm going to start here with this. These 3 lines of code actually are kind of the heart of everything. And then we can add or fill in as needed. Okay. So how does this work? So we have first of all, we have 2 for loops. 1, 2, 3. This second for loop essentially grabs every sample in X train. There are 120 samples in X train. So we're going to grab the first one, the second one, the third one in a loop. But if you notice, this is a nested loop within this loop. This loop essentially just goes from 1 to 1,000. So what this is doing is that we're showing that, we have a neural network and we're showing it we're showing all the samples in X train to the neural network, but we repeat that 1,000 times. So this is one of the criticisms of neural networks, right? So humans, for instance, if you just need to see something like once, maybe twice, maybe a third time, and you understand it. Neural networks need to see the same thing 1,000 times sometimes, right, in the beginning. And so that's essentially what's happening here. You take the whole data set and you show it to the neural network repeatedly 1,000 times. And that might help the model to do better, okay? So you'll see this a lot. In a lot of the examples that we're going to do this semester, we're going to have the 2 for loops. Any questions about that? All right, great. So now, if you notice over here, this is the heart of a neural network, right there. It's a simple equation that multiplies. So you can see it's got this thing called NP dot, or the matrix, a dot product or a matrix multiplication, like the examples you did, right? And we're multiplying what? The vector of the X values times this vector of weights, right? Plus this value called a bias. And this is the inference equation that gives us the result, which is called a linear product here. So tying this back to the hardware that I provided here. So essentially, Xi is the data here, right? The switches that represent the T or whatever it is, the image. Okay? Everyone with me? All right. Weights, the thing that you're multiplying with, is the knobs. So you essentially multiply this times that. So this times that, and then you just add an additional parameter called a bias, all right, which is another value that you have to learn. And that's it. Once you do that, then you get this linear product here, which represents this over here, whether it's greater than 0 or less than 0. That's it. So if you want, when you're doing your website, right, and you're building your website to represent this and for it to work, you'll have to code this equation in. Now, I'm not going to ask you necessarily to learn. Maybe you can have the weights already and you just predict. That's really all I'm asking you to do the prediction, which means you know the right combination of weights, but or the right combination of knobs, of turning the knobs. And that has to happen, using some kind of an algorithm that we're going to use in this example. Any questions? Questions? Really? No questions? All this makes sense? Awesome. All right, great. So let's continue then. So let's continue with the process. But this is that, I'll write in here. this is, you'll hear me say this, this is the inference equation. You know, to give you an example, whenever how many of you have used ChatGPT? A lot of you, right? Whenever you use ChatGPT, what you're using is the inference equation. Because OpenAI and that company, they've done the training already. They did it in their clusters of thousands of GPUs, and they found the right combination of knobs. That's done. It's stored in a file. It's 600 or some billion parameters. And then when you go to the ChatGPT, all you're using is their inference function. Obviously, their inference function is massive, like massive. And we'll see that as we start progressing in the semester, you'll see me adding more complexity to these things. But today, let's not even worry about that, and let's just try to understand this very simple idea. And I will draw in a second also the neural network and what that looks like, essentially. Okay? All right, so very important. So this is the data. These are the weights. These weights we have to adjust, so we need to update these weights. And so that is called the update rule, which is, we'll see very nicely how it was derived initially by Widrow in a very nice way, okay? So they use some math in a very clever way. But yeah, that's it. All right, so no questions. Let's keep going then. So now, if you notice, Xi is really, I already have it available because I already have X-train, 150 by 2. So every time I grab something out of X-train, it's a 1 row by 2 column vector, right, that I'm slicing out, right? So every time I'm grabbing one of those, that's Xi. This is just, for IDX, comma, Xi in enumerate, this just gives me the index position. So 1, 2, 3, 4, 5, all the way to 120. So I have that. And then these two parameters, weights and biases, are variables that I need to define that I'm going to be updating, essentially, the knobs. All right, so let's do that part. Let's go over here and let's take a look here. I'm going to grab these two. Oops. And I'm actually going to add a little comment here. And I'm just going to say, defining the knobs. Okay. So I'm going to define the knobs here, and then there they are. So the weights, okay, and the bias. So the bias is only one value. Why? Because the bias is really just connected to the output, and we're only predicting one output, right? Which is the value of that needle that moves from +1 to -1. So really, we only need one variable for that. We're not predicting more than that. The weights have to do with the image, right? If I was using data like this one, then my images would be 4 by 4, which means I have to spaghettify them, which means I would have vectors of 4 times 4, 16, right? So it would be 16, right? So vectors of 16. But to keep it simple, I just made it vectors of 2. Do you see but I could have made it vectors of 16 to be consistent with this example, okay? Any questions about that? All right, great. So we have an image, spaghettify it, it would be 16. But in my example, they're just 2. Okay, I'm using, also you learned this from the 70 problems, right? NP.zeros, you learn how to create those vectors, and they will hold 2 values. So why 2 values? Because my vectors are really just, let's say, 2 LED lights, which means I have 2 knobs, right? And so I just need values for each of those 2 knobs. So I've defined that, and if you notice at the end, the thing that I'm returning is the weights and the biases, so that later when I want to do inference, I'm just going to invoke this exact same function, but I will have these values already learned. Whereas initially right now, if I try to do some inference with this, those variables are random or they're actually zeros because I use zeros here, so it's not going to work. But once I've done the training, these have the correct values, the position of the knobs, potentiometers, and then I can do the right prediction. All right, so let's keep going then. So I've created these two variables. I think this actually will not break, so we might run it, right? So let's do a print statement of xi, right? We can also do a print statement of the weights if you'd like. Weights. And we can do a print statement of the bias. Just like, okay. So it's going to do the operation. So let's also take a look at linear product and what that looks like. Linear underscore product, just like that. All right, and I'm going to, I like to add an input statement here, and that just halts the program until I press enter. So that way I can kind of like every iteration look at the output. All right, so let's see if this works. Let's run it. So I'm going to save first, in class Perceptron, run the function, so no errors. Just skip data. Print to shapes, got my values. You know what I want to do also? I'm going to print X just so that you guys can see. So X before splitting, and I'm going to slice it, right? So I'm going to do the first 5 rows. Oops. The first 5 rows and then all the columns, okay? So they should be about 5 by 2. And we should be able to see what the values look like. And you can see that. So that's my data, which is equivalent to the values in these LEDs. Because these are LEDs, these are just these switches, so they're just binary, right? In my example, they're real value numbers. Got it? All right. So we did that part. So we look at the data. Now I'm going to do the split. Print to shapes. All right, now we're ready. I can also print these at the end. And you'll see that, well, it's going to halt before, but let's see what. All right, so I'm going to run this one. Okay, great. So as you can see, that's the first iteration. It grabs the value in X, the first of the 120, right? It grabs the first value, like an image of a T or an L, essentially. And then I'm printing the weights and the biases and the predicted value. You see that? So the weights are zeros, the bias is 0, the predicted value as expected would be 0 for that function because we don't have a good set of weights. And that's going to continue to happen because we're not doing anything to the weights and the biases, right? We need to add some kind of a learning rule. And so that's what I'm going to add now is the training part, right? And this was the very first set of ideas on training this done by Rosenblatt. But that had limitations, of course, and that was improved upon by Widrow and then Geoffrey Hinton. So you guys know that Geoffrey Hinton won the Nobel Prize in Physics for solving this problem. And it might surprise you, there's only one technique to train all neural networks, and it's this one. There isn't a second one or a third one, just one. And it's this. And it took from 1940 to 1984, so that's about 40 years to solve. Although there were a few AI winters in there. All right, so anyway, so you see the process, right? If I keep doing it, I'm grabbing X's, but the weights and the biases are not changing because I'm not doing anything to them, and therefore the outcome is still 0, and it's nothing is happening. So now let's kill this. So now we need to go obviously to the fit function and start to make some improvements to it, right? So let's go back to my provided example here. So let's see. So I will need a learning rate, but I'll talk about that in a second. These are just for like capturing information that we can plot. So really essentially, if you look, this section here is the learning rule that we're going to use. And this was derived mathematically, right? But so we're going to take a look at that later. But for now, let's just use the equation here. So I'm going to, and I'll make some modifications. So I'll copy this whole thing. And that's how the model is going to learn. All right. So you can see that. So what's the basic idea? The basic idea was that they would compare the predicted value of the perceptron to the real value. That's it. And then try to minimize some kind of an error. That's it. That's like the magic of this whole thing. You have the model and it says it's a 3. Was it? And then you ask yourself, was it a 3 for this image? Or going back to the analogy of the L, right? And the T. You give it a T and it says it's an L, but it was a T, so that's an error. That has a higher error than if I give it a T and it says it's a T, compared to the fact that it is a T, so then a lower error. You guys see that? That's it. And a lot of what we're going to do this semester is based on that very idea of comparing the predicted to the real. There's just some like additional formulas going on. So let's read through this. So it says, essentially, we're going to compare the predicted to the real. And that's why we have X train, X test, Y train, Y test. We're comparing the Y train values, right? So, that's why we have X and Y. We're comparing the Y values to the predicted Y values. So compare predicted to real. This is called the Perceptron update rule. Okay, so this is the rule that essentially does everything. Okay. We have here, I'll get rid of that. So it's broken up into parts. So, usually you'll see this as a single equation. And I'm going to comment this one out too, because that's not related to this. So let me move this actually. Right. So these 4 things are it. Okay, so let's analyze it. We're taking the predicted value. You see that? This is the predicted value, Y pred. And we're going to the name changes from linear product to Y pred because I need to run it through something called the activation function. We'll cover that in a second. Just assume linear product is the same as Y pred for now, okay? Just notice it goes through this activation function. But essentially, once we have Y pred, we compare it to Y real, okay? We can also square this, although it's not squared here, like that, okay? So let's just leave it as is for now, but know that we can do that. And we need to, you'll see this a lot. So we need to understand why all these little things are done. They're improvements. But anyway, we predict we compare the predicted to the real, and let's call that loss, okay? Which is repeated here, Y pred minus Y train, take the difference of that. We multiply that times something called the learning rate, which is just some value like 0.01. Okay. And then that gives us this thing called update. And then update is used to essentially update the weights and the bias. So if you look, this is the weights, which initially were what? Zeros, right? And then, so this is the update rule. So we take the old weights, right? And that's going to give us the new weights, but we need to modify them. And then we need to essentially add or subtract something from weights. See that? So this update is this variable. So another way of thinking about it is we take the weights and we always add 0.01 to it. Add or subtract 0.01 to it. The thing is, sometimes we want to add it, sometimes we want to subtract it, and then that's what this parameter provides. Like this, the direction that we want to follow. And then we multiply it times xi. This is so you'll ask me why this is, why is it like this? So we have to do some math calculation, right, to arrive at this formula. But for now, let's just assume this is the right formula to use. And then later I'll show you guys how they came up with this formula. Okay, so the formula is essentially this times xi here. So I could have just, if you notice, I could have just done, to keep it as one single formula, could have done that. Plug this in. Like that. All right, so that's the formula, the update rule, okay? So let me comment that out, which would also be this one here. Like that. All right, so essentially we have the weights, we have the biases, and we're constantly updating them by adding a little value, and we just need to know if we're going to add or subtract to that. That's it. That's the whole idea with this process, okay? So let me actually, now that we've talked about it a little bit, let me redo this part. And later we'll derive why that is. I'll keep it as I had it. All right, breaking it up into parts. All right, so here it is. So the learning rate. So now what is this learning rate? So this learning rate is just a value that you define. It's an important value. So I have a good analogy for that. Let's define it up here somewhere. And it's going to be 0.01. So what is the learning rate? Let's go back to our hardware. So when we're turning these knobs, right, the learning rate is essentially by how much we turn that knob. So for instance, let's say I have this knob, right? So I could do this and then this. You guys see that? It's a very tiny learning rate. Or I can do this. You see that? That's a very big turn on the knob. That's the learning rate. You see that? Obviously, now imagine a very, very, very small turn. So if I keep doing that with a very tiny turn, then it would take me 1,000 years to figure it out. If I do always this, I may never arrive at the right answer because it's just too pronounced. So you just have to find like a correct turn of the knob. You're consistent with that. More advanced algorithms will actually adjust that turn. So maybe they start with big ones, and then after a while of training, they make it smaller. That's called an adjustable learning rate. Decaying learning rates also. So that's possible. But initially, and definitely in our example, this turn of the knob is fixed. Just, all right? Always the same and consistent. So if you selected, and you can, I encourage you once we finish the script to try this out. I encourage you to try that. Try it out and see how long it takes to learn, how well it learns. Or also, this is already a very how many? What was this? 0.01? Yeah, 0.01. So I encourage you to try 0.1 and see what happens, right? So try the extremes, but essentially that's what that means. So we've defined the learning rate. So that means, great, we've got this one. We know that we need to predict Y-pred, so we'll take a look at that in a second. We have Y-train, which is the label. Y-train is a list, right? So IDX is just the index. Because we're using the enumerate here, and we're going from 1 to 120, when we're at 17, we're at index 17, so we just grab the corresponding label for index 17. You guys remember that they map, right? So you have 120 samples, 120 labels. You grab sample 17, you need to grab label 17. All right, so that's what's happening there. So I have in Y-pred the predicted, and in this one I have the real value. I take the difference of it, multiply it times the learning rate, which is 0.01, and that gives me the update, and then I just take update and multiply it times xi, which, by the way, is the value. So as I said, this part of the equation you may be wondering why, right? So I need to do a derivation of this, so we'll do that later. But just trust me that this is the equation right now. All right, so now one thing I want you to notice, which is really important. What is weights? Weights is a vector of size what? 2, right? Size 2. And this value is potentially just a scalar, a number like 0.05, something like that. But this one is a vector, right? Xi, we know, is of size 2 also. So if you notice, size 2 multiplied times the update, right? And that value is then added or subtracted to the original weight. So a vector of 2 minus a vector of 2, essentially. You see that? So this is a vector of 2, the weights, because we defined it here as 2, and this is a vector of 2. So we can update both weights in one shot. Is that clear? All right, great. And then we do the update for the bias. Remember that the bias is only linked to the final layer, not the input, but the output part. So we are only predicting one thing, is it positive or negative? So we just need to update it like this. And that's it. This is the whole perceptron. Okay? So the questions that you might want to write down is, why do we have this little xi, for instance, there in the equation? Otherwise, everything else should make sense. And as I said, I'll have to derive this a little bit. This is the part that uses calculus, but it should be straightforward to see. They actually figured out that it was just this equation. And this was done by Widrow. So this was done by, so one of the people. All right, so let's test this. Let's go ahead and test this one and see how it works. So I'm going to leave the input in here just so that we can see that the values are changing, right? So that's one of the things we want to try out. So save this. I'm going to hit run. Got my data. All right, so that's the first iteration. Notice that the values are zeros. Oops, okay. Y-pred is not defined, and that's because the value that comes in from linear product needs to go through one function called the activation function. So that's one part that I have not defined yet. So let's go over here. You can see, Control copy. My linear product, this one here, that value, whatever it is, will go into this function, activation function, and then produce ypret. The activation function is a key component of neural networks, okay? One of the first activation functions was defined by Macaulay. Okay, so for this, I need to go back to the notes. So I'm going to go back to machine learning foundations, neural nets, the perceptron here, and you can see these are the activation functions. All right. The one that we're going to use, the very first one is the Macaulay. This person, Macaulay and Pitts, they call it a unit step function, essentially, right? So for the value in X, it maps it to a value in Y. Do you guys see that? So that's essentially what's happening there. Whatever the value is. So if it's less than 1, let's say -3, -0.3, -5, whatever it is, what does it become? -1. Any negative value is now always -1. If it's 0.2, 0.3, 0.5, 0.05, whatever positive value it is, it becomes what? 1. So it's whatever the value is in the x-axis, now it's translated to a value in the y-axis. And if you notice, this y-axis only has 1 or -1. Make sense? And you can see that here also written out. If c greater than 0 is +1, otherwise -1. So what are these activation functions they're simple, like they're straightforward, but they're so important to neural networks. They're like one essential component that neural networks need to have. As you see here, there's many of them, right? And later on, we're going to start using sigmoids and ReLUs and all that stuff, but they're essentially always doing the same thing, all right? Mapping whatever value you get into something else. Got it, guys? Does that make sense? Yeah. Perfect. All right, so that stepping function is needed here. So let's define it. We need to define the activation function. So I'm going to go over here, and I just have it somewhere in here. There it is. And let's test it out so that you guys see the behavior of it. I'm just going to plug it in here. So paste it. So define the activation. Notice that it takes a value z. It uses numpy.where, basically, and it provides a value 1 to 0. Why 1 to 0? Remember that my labels are 1 to 0. If I had made them 1 and -1, then use 1 and -1. Does that make sense? It's almost like an if statement. Kind of, okay? So let's try it out. So I'm going to add a cell here. I'm going to run this one here. And then I'm just going to say activation function, copy. Okay, so I'm going to give it a number, -0.3. 0. Do you see that? And if I do plus, it's just that. Essentially. So whatever value I put in there, I could put a 0.7, still 1. And that's what an activation function does. And that actually is really important. Okay, that's a really important functionality of in neural networks. Any questions with that idea? All right, all neural networks will have these things. So now hopefully the code will run. So let me save it here. Hit run. Unexpected indent. So I have, yeah. All right, let's try it one more time. Okay, so the function, no errors. It ran this time. So let's keep going then. Data set. All right, so it's running now. That's the first iteration. Weights and biases are zeros. So you can see that, you know, weights and biases are 0, and the predicted value is also 0. List losses is not defined. Okay, so where's list losses? This one. Let me comment it. That list losses is just a way of looking at the loss value so I can plot it later, but I can ignore it for now, all right? I don't need to worry about that. We're only focused on the algorithm. All right, so let's try it again. All right, let's hit enter. All right, there we go. So as you can see, initially all the values were 0. Now we're starting to get something, right? In this iteration, we gave it a second x value, but now we are updating the x's and the weights and the biases, right? And we're predicting and comparing the prediction to the real. This is the prediction. So we would want then see, so now you can see the weights are changing, right? So you guys can see it goes from 0.19 to 0.03, predicted value. Do you guys see that? Does that make sense? That's it. That's machine learning. That's ChatGPT right there. It's a little bit more to it. But essentially, though, that's it. You want to learn these weights and biases. Someone made the joke, I think it was Elon Musk or someone, that people say ChatGPT and AI is going to kill us all, right? Because they're living beings or something. ChatGPT is essentially that, except there's 671 billion. Oh, that's it. Some architecture. Once you use the inference model, it's just an architecture, and those values are it. Like its soul, its essence, whatever you want to call it, is that. Before that, you just have architecture. That's nothing. What you need is these weights going through this architecture. Okay? A good analogy I can give you, for instance, is going from one city to another. You go through many roads and many cities in between, but what's the right path to get from one to the other? It's a similar idea. So anyway, I'm obviously just I'm just iterating through this. So you can see we can just explore all of it, and we look at the values, right? See that? And that's it, And so now what I want to do is I want to measure performance, right? So obviously, I trust that that update rule is the right one because Widrow tells me that that's the right one because he and his student derived it, and that's it. Okay, so I gave it some data, it learned, but I want to measure performance. Exactly what you guys are doing in your WECA homework, exactly what we did in the KNN homework, but now I'm just going to do it here. I need to add the little components to measure performance. So let's go ahead and do that. I'm going to stop this loop. All right. I'm going to go back to this. I'm going to remove all these print statements because I don't need them for the training. That was just for debugging purposes. I'm going to remove this. Okay. So now what we want essentially is we want these weights and biases printed out. So let's run the whole script. I'm going to do run. Got my fit function. Got my data. Save it. Okay. So it's training. Notice that this is a solid. Oh, it finished now. So the fit function finished. So now I'm going to print weights and I'm going to print bias. And essentially I've done 1,000 iterations where every iteration I gave the fit function or the model all the data. So after all that training, which today for ChatGPT is 1,000 GPUs and all the text in the internet, right? That's the same thing that we're doing here, only with a much smaller data set. And so I have arrived at this, and this is really valuable. This is the valuation of OpenAI of $10 billion right now, right? These weights, because they are actually what give the intelligence. So now what we want to do is so notice the bias is 0.12 according to this. So what I'm going to do now is test this, just perform inference on the test set. And I'm going to predict, given the test set data, I'm going to predict the labels and then compare to the real labels and measure the performance, see if it's good or bad. Because I have the weights and the biases here. So how do we do that? We know we have the test set, so I can just use a little function called predict. So I have predict. Predict takes the X test data, right? The 30 samples that I left out. It'll take the weights and the biases, which are these values here that I just finished training. And notice we just used the exact same equation that I had in here, right? So it makes sense because when I was training, I would get data and some random weights and I would predict. And then based on that, I was updating those weights and learning. Now that I have the right weights, we would expect this to be pretty good. So we just use the exact same equation, NP dot. We're going to take the X test, right, times the weights plus the bias, which is this exact same equation here. And that gives us our linear product. We still need to run that through the activation function to make it 0 or 1 in our particular case. And then that's going to be at my Y red. You see that but of the test set. I also need a function to compare the predicted to the real, right? So that's going to be my accuracy function here, which is this one. All right, and I'm just going to compare the difference between the predicted and the real and sum the values, right? And that should give me how accurate the model is, right? And then just essentially, so this is where I predicted, so then I just need to do this, right? So notice I'm going to give it the X test data. I'm going to give it the weights and the biases. Predict is this function that I define here, and it's going to give me Y prime for the test set. And then I'm just going to plug those values into my accuracy function, and I will know if the model was able to learn or if it wasn't using the Perceptron approach. So we'll print these, but essentially it's this one here. All right, so let's try it. Let's see if it works. So I'm going to add the predict function. I'm going to add the accuracy, no errors. Now I'm going to predict on the test set. Predictions are there. Let's take a look at YPred. There's only 20 samples in there, so I can actually inspect them visually, right? Although if you had 100,000 samples, you can't do that. You'd have to use the metric. What do I want to compare this to? I want to compare it to Y-test, which is when we split the data 80%, 20%, we left these out for the test set. So let's take a look. Y-test. What do you guys think? Y-pred compared to Y-test, do they look similar? Do you see any errors at all? Like maybe one was wrong? So it's almost perfect, right? Almost perfect. But we can corroborate so we're going to plug in YPred and Y-test into the accuracy function. And this is going to tell us 1%. That means 100% accuracy. It worked. Do you see that? This is just a perceptron algorithm, which is the simplest neural network, but at the same time, give me a sec. At the same time, everything we're going to do with neural networks, all the way to very deep neural networks, will be very consistent. Sir.
Would overfitting fit into this at all?
So overfitting is when, so here's the answer. Let's say that I measure accuracy of the predicted values in the train set. Like I train it, and then I actually would here, instead of putting in X test, I put in X train again. So what that means is I train the data on X train, and then I'm evaluating on train set. So it gives me a 1, like 100%. But when I run it on this, it gives me 0.60%. That's the overfitting part. So it was overfitted on the train set, and it did not generalize to the test set. That's what overfitting.
Okay.
You don't want that, right? So think of the thing when you're competing and you have this data set and you built a model and it does really well on your train set and you're really excited. But then you get to the competition, they give you the test set and you get 50%. So it's good on the train set, but it did not generalize to the test set. It overfit to the train set. So maybe it would have been better for you to get like 80% on your tests on your train set. And then here, maybe you would have gotten like a 0.70 because it wasn't so focused on what it saw and it could generalize to unseen things. Got it? All right. Yeah, so that's it actually. It's good stopping point actually. So this is the perceptron. This is the first algorithm that we've covered in the neural networks sequence. I will on Wednesday I will continue with this one. I'll add things like plotting and things like that just so that we can collect more data, but essentially it's done, right? We did all the basics. And then, of course, I will then do a little bit of like the notes so that we can see where does the update rule come from? How was that derived? And also we will cover the homework. So I want you, so hopefully now it makes sense, right? I want you to implement a website. So your website essentially needs to be a lot like this. That equation needs to be in your website, but you also need to learn the weights, right? And then you're going to make it to resemble you're going to make it to resemble the machine that I provided, right? So I want you to, so it's got to have, flip the switches, make the T, and predict the things. Okay? Does that make sense, guys? And I'll show you how to, you guys, all of you took 110 already, right? You've taken 110 and you know JavaScript, but if you don't want to use that, I'll show you something called PyScript. So essentially you could write in Python, you just put PyScript tags and you can run it on HTML. Okay, so we'll do that on Wednesday. All right, guys, have a good rest of your day. We'll stop here for today.
My first time working.